Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. Picture this moment with me. It's late evening. You're sitting somewhere quiet, maybe on a balcony, maybe by a window that looks out over a sleeping city. In your hands, there's a cup of tea, still steaming, the warmth radiating against your palms. Above you, if you're lucky enough to be away from the lights, stars scatter across the darkness like ancient whispers frozen in time. You take a sip. The tea is hot, almost too hot, but in a few minutes, it won't be. You know this. You've always known this. The heat will leave the cup, will blend into the air around you, will become part of the quiet coolness of the night. And once it does, it will never gather itself back together. The tea will never spontaneously reheat itself. The warmth, once scattered, stays scattered. This simple moment, this cooling cup of tea, holds within it one of the deepest mysteries in all of physics. Think about the fundamental laws that govern our universe. Most of them don't care about direction. They work the same way forward or backward in time. An electron doesn't know if it's moving toward the future or the past. A collision between two atoms looks perfectly sensible whether you play the footage forward or in reverse. The mathematics of motion, the dance of particles, the waves of light, all of these are, at their core, reversible. And yet, you've never seen a broken glass reassemble itself. You've never watched smoke flow back into a candle. You've never witnessed a river flowing uphill on its own, or heat moving from something cold to something hot without help. You've never seen time run backward. Why? Why does the universe have a direction? Why does time have an arrow? Why do some things happen easily in one direction, but seem impossible in the other? The answer lies in a single concept. A concept that's frequently misunderstood, often oversimplified, sometimes feared, and yet absolutely fundamental to everything that exists. It's a concept that governs the behavior of engines and stars. That explains why we age, why we remember the past but not the future, why life exists at all, and why the universe itself has a story with a beginning, a middle, and perhaps an end. That concept is entropy. You've probably heard the word before. Maybe in a physics class, maybe in a documentary, maybe in casual conversation. And chances are, you heard it described as disorder or chaos. You might have heard that entropy is always increasing. that the universe is sliding toward randomness, toward some kind of cosmic messiness. But that's not quite right. That definition, while not entirely wrong, misses something profound, something beautiful. Entropy isn't really about disorder in the way we usually think of disorder. It's not about messiness. It's not about things falling apart or becoming chaotic. Entropy is about something far more subtle, far more fundamental. It's about the spreading of energy, the distribution of possibility, the quiet, inexorable flow from concentration to dispersal, from bundled to scattered, from here to everywhere. And once you truly understand entropy, once you see it not as destruction but as transformation, you begin to see the entire universe differently. You begin to understand why engines can never be perfectly efficient, why perpetual motion machines are impossible, why the sun gives us more than just energy, why life exists, why complexity arises, why memories only point backward, and why time itself flows in only one direction. Entropy doesn't just describe disorder. It describes the silent flow of the universe itself, the gentle, irreversible drift from what was to what must be. The reason why this moment, right now, as you read these words, is different from every moment that came before, and every moment that will come after. This is the story of entropy, not as a villain in the cosmic drama, not as a force of destruction, but as the quiet choreographer of everything that happens. The reason stars shine, engines turn, and hearts beat. The reason you exist at all. So let's begin at the beginning. Let's start with a simple question. That isn't simple at all. What does Earth really get from the sun? If you stopped people on the street and asked them this question, you'd get a variety of answers. Most would be correct, in their own way. Light, someone might say, and they'd be right. The sun bathes Earth in light, visible light that lets us see. That paints the sky blue during the day, and gold at sunset. Heat, another person would answer. Also true. The sun warms our planet, keeps the oceans liquid, drives the winds, melts the ice, makes summer different from winter. Energy, a more scientifically minded person might offer. Absolutely correct. The sun is our primary energy source, the power behind nearly every process on Earth. Vitamin D, someone else might joke. Well, technically, the sun provides the ultraviolet radiation that helps our skin produce vitamin D. So even this playful answer has truth in it. But here's where things get interesting. Here's where a simple question opens a door to something profound. Earth does receive all these things from the sun. Energy, light, heat, all flowing to us across 93 million miles of empty space. About 173,000 terawatts of solar power strike our planet at any given moment. That's more energy hitting Earth in 1 hour than all of humanity uses in an entire year. But, and this is crucial, Earth doesn't keep that energy. Our planet isn't getting hotter and hotter with each passing day. We're not accumulating all that solar energy like a battery that never drains. Instead, Earth radiates almost exactly the same amount of energy back out into space, mostly in the form of infrared radiation, heat that glows invisibly outward from our atmosphere, from our oceans, from the ground beneath our feet. Energy comes in, energy goes out. The amount is roughly balanced. So if Earth receives energy from the Sun, and then sends approximately the same amount of energy back into space, what are we actually getting? What's the net gain? This is not a trivial question. This is one of those moments where simple arithmetic leads to profound physics. According to the law of conservation of energy, one of the most fundamental principles in all of science, energy cannot be created or destroyed. It can only change form. It can only move from place to place. The total amount of energy in an isolated system remains constant. Earth and the Sun, taken together with the surrounding space, form roughly an isolated system. Energy flows from the Sun to Earth. Energy flows from Earth into space. If the amounts are equal, then the accounting is balanced. No energy is gained. No energy is lost. And yet, something extraordinary is happening on this planet. Plants are growing. Animals are moving. Weather patterns are churning. Ocean currents are flowing. You are thinking. I am writing. Civilizations are rising and falling. All of this requires energy. All of this requires power. Where is that power coming from? If the energy budget is balanced, the answer is one of the most beautiful insights in physics. And it leads us directly to entropy. What Earth receives from the Sun is not just energy. What we receive is low-entropy energy. Let me paint you a picture of what this means. Imagine energy as water. The Sun sends us water. We use the water for various purposes. And then we send the same amount of water back out into space. The volume is conserved. The mass is the same. And yet, the water we receive is fundamentally different from the water we return. The water coming from the Sun arrives concentrated, bundled, organized. It comes as a powerful, focused stream, like water rushing down from a mountain spring, contained in a narrow channel, full of potential. The water we return is spread out, dispersed, diluted. It leaves as a gentle mist, distributed across a vast area, each droplet barely moving, the concentration gone, the potential exhausted. This is entropy. This is the key difference. The Sun sends us roughly 1 unit of highly concentrated, high-energy photons, mostly in the visible and ultraviolet part of the spectrum. These are tight packets of energy, bundled into small volumes, organized, concentrated. Earth absorbs this energy, uses it to power everything from photosynthesis to hurricanes, and then radiates it back out as roughly 20 units of lower energy, infrared photons. Same total energy, but now it's spread across many more particles, distributed across a much larger portion of the electromagnetic spectrum. diluted. Think of it like this. You could receive your monthly salary as a single $1,000 bill, or you could receive it as $1,001 bills. The total value is the same. The purchasing power, mathematically, is identical. But there's a difference in how concentrated that value is, how organized, how easy it is to use for certain purposes. The sun gives us energy in the form of a few very valuable bills. We use that value to run the complex machinery of life and climate. And then we return the same value in the form of many, many smaller bills, spread out, dispersed, less useful for doing further work. This is what low entropy means in the context of energy. It means concentrated, bundled, organized, full of potential to cause change, to do work, to make things happen. And this is what Earth truly receives from the sun. Not just energy. Energy is everywhere. Energy is conserved. Energy never disappears. What we receive is the opportunity to use organized energy. We receive the gift of low entropy. Everything that happens on Earth, every leaf that grows, every animal that hunts, every wave that crashes, every thought you think, is powered by this flow. This one-way journey from concentrated to dispersed, from organized to spread out, from low entropy to high entropy. The sun doesn't just give us energy. It gives us the ability to do something with energy. It gives us usable energy. It gives us order. And in doing so, it reveals a fundamental truth about the universe. That order, structure, complexity, and life itself are not violations of the rules of physics. They're consequences of the flow of entropy. They're what happens in the middle, in the transition, as energy spreads from where it's concentrated to where it's not. But to understand this fully, we need to go back in time, back to France in the early 1800s, to a young engineer who was trying to understand something that seemed completely unrelated. Why steam engines could never be perfectly efficient. His name was Sadi Carnot, and his work would eventually help us understand not just engines, but the universe itself. The year is 1824. France is still recovering from the Napoleonic Wars. The emperor is gone, exiled and then dead, and the country is trying to find its footing in a rapidly changing world. But one legacy of Napoleon's era remains dominant: the steam engine. These magnificent machines, hissing, clanking, powerful, are beginning to transform everything. They power factories. They drive mills. They pump water from mines. In Britain, they're starting to pull trains across the countryside. The Industrial Revolution is underway, and steam is the force driving it forward. For France, this is both an opportunity and a problem. British steam engines are more efficient than French ones. They extract more useful work from the same amount of coal. And in an era where coal is expensive, and industrial power means economic and military strength, Efficiency matters enormously. Enter Sadi Carnot, a young French military engineer. He's 28 years old, brilliant, curious, and disturbed by a fundamental question. Why can't we build a perfect engine? Why does some of the heat from burning coal always seem to go to waste? Is there a theoretical limit to how efficient an engine can be? Or is it just a matter of better engineering? These might seem like practical questions, engineering questions, but Carnot's investigation would reveal something far deeper. Something about the fundamental nature of heat, work, and energy itself. Let me describe to you the thought experiment that Carnot devised. It's simple enough to visualize, but profound enough to change physics forever. Imagine two metal bars. One is hot. Perhaps it's been sitting in fire, and its atoms are vibrating intensely, jittering with thermal energy. The other bar is cold. Perhaps it's been sitting in ice water, its atoms moving sluggishly, comparatively still. Now place these two bars at opposite ends of a sealed chamber. Inside the chamber, there's air and a movable piston, a cylinder that can slide back and forth. Here's what happens. You bring the hot bar into contact with one side of the chamber. Heat flows from the bar into the air inside. The air molecules near the hot bar start moving faster, bouncing around more vigorously. As they do, they push against the piston. The piston moves. Perhaps it's connected to a rod, which turns a wheel, which performs some useful work, lifting a weight, grinding grain, pumping water, whatever you need. But here's the crucial point. For the piston to complete its cycle, to return to its starting position, and be ready to extract more work, you need to bring the cold bar into contact with the other side of the chamber. You need to cool the air back down. Heat flows out of the air and into the cold bar. The air molecules slow down. The piston returns. The cycle repeats. Heat in from the hot reservoir. Work out via the moving piston. Heat out to the cold reservoir. Return to start. This is a heat engine in its most basic form. And Carnot's genius was to ask, what is the maximum possible efficiency of such an engine? He imagined a perfect engine. No friction, no leaks, no losses to sound or vibration. Every part moving with ideal smoothness. The cycle running infinitely slowly, maintaining perfect equilibrium at every step. A theoretical ideal. And even this perfect engine, Carnot discovered, could not convert all of the heat from the hot reservoir into useful work. Some heat had to be discarded into the cold reservoir. Always, necessarily, as a matter of fundamental principle. The efficiency depended only on the temperatures of the two reservoirs. The hotter the hot source, and the colder the cold sink, the more efficient the engine could be. But it could never reach 100%. Never. Why not? At the time, Carnot didn't have a complete answer. The concept of energy conservation wasn't yet fully understood. The nature of heat itself was still debated. Was it a fluid, a substance, a vibration? But Carnot's insight was correct, and it pointed towards something profound. To extract useful work from heat, you need a difference, a gradient, a flow from hot to cold. Heat naturally wants to spread from regions of high temperature to regions of low temperature. And as it does so, you can harness that flow to do work, like placing a water wheel beneath a waterfall. But just like you can't extract energy from water that's already at the bottom of the waterfall, already at the same level as everything around it, you can't extract useful work from heat that's already spread out evenly, already at equilibrium. The heat that gets discarded into the cold reservoir isn't destroyed. Remember, energy is conserved. It still exists. It's still heat, but it's now at a lower temperature, closer to equilibrium with its surroundings, less able to flow, less able to cause change. It's become higher entropy heat. Carnot died young, tragically young, at age 36, of cholera. He never saw his work fully appreciated, but the principle he discovered, that there's a fundamental limit to the efficiency of heat engines, a limit determined by temperature differences, would become one of the cornerstones of thermodynamics. It would help us understand why perpetual motion machines are impossible, why you can't build an engine that runs forever without external input, why even the most perfect machine must always waste some energy. And it would lead directly to the next great insight. That temperature itself has an absolute meaning, an absolute zero, below which you cannot go. William Thomson, later to become Lord Kelvin, was born in Belfast in 1824, the same year Carnot published his treatise on heat engines. By the time he was a young man studying at Cambridge, the scientific world was beginning to grasp the implications of Carnot's work. Kelvin became fascinated by temperature, not just as a practical measure of hot and cold, but as a fundamental property of matter. And he realized something remarkable. If efficiency of a heat engine depends on the ratio of temperatures, and if there's a lowest possible efficiency, zero, when no work is extracted, then there must be a lowest possible temperature. Think about what temperature really means at the atomic level. It's a measure of motion. In a hot gas, molecules zip around frantically, colliding with tremendous speed. In a cold gas, they move more slowly, more gently. Temperature is just average kinetic energy, the energy of motion, translated into a number, which means there's a natural floor, a bottom limit. Imagine cooling something down further and further. The molecules slow down. Their vibrations diminish. Their movement becomes more and more sluggish. And theoretically, at some point, they would reach the slowest possible motion consistent with quantum mechanics. Not complete stillness. Quantum mechanics doesn't allow that. The uncertainty principle means particles always have some residual motion. some zero-point energy, but as close to stillness as the laws of physics permit. Kelvin calculated where this point would be using the ideal gas law and Carnot's principles. He found that it corresponded to negative 273.15 degrees Celsius, negative 459.67 degrees Fahrenheit. This became the 0 point of the Kelvin scale. Absolute zero, the coldest possible temperature, the point at which thermal energy reaches its minimum. In Kelvin's scale, there are no negative numbers. 0 Kelvin is absolute zero. Room temperature is about 293 Kelvin. Water freezes at 273 Kelvin. The surface of the Sun is about 5,800 Kelvin. And crucially, the efficiency of a Carnot engine can be expressed beautifully in these absolute temperatures. Efficiency equals 1 minus the ratio of the cold temperature to the hot temperature. If the cold reservoir is at 300 Kelvin, roughly room temperature, and the hot reservoir is at 600 Kelvin, about the temperature of a candle flame, then the maximum possible efficiency is 1 minus 300 divided by 600, which equals 0.5, or 50%. Half the heat energy becomes work. Half must be discarded. If you want higher efficiency, you need either a hotter hot source, or a colder cold sink, or both. The only way to reach perfect efficiency, 100%, would be if the cold reservoir were at absolute zero. But absolute zero is unreachable. It's a limit you can approach, but never quite touch. The closer you get, the more difficult it becomes to extract any more heat. It's like an asymptote in mathematics. You can get arbitrarily close, but never arrive. This makes perfect efficiency impossible. Always. As a matter of fundamental principle. And this impossibility is deeply connected to entropy, because what Kelvin was really discovering, though he didn't yet have the full vocabulary to express it, was that heat and work are different forms of energy. Heat is energy that's already somewhat dispersed, already spread among many particles in random motion. Work is energy that's organized, directed, capable of causing systematic change. Converting work into heat is easy. Rub your hands together. The organized motion of your hands moving past each other becomes the random motion of molecules in your skin. Friction converts work into heat with perfect efficiency. But converting heat into work is hard. You need a gradient, a difference, a flow from concentrated to dispersed. And even then, you can never convert all of the heat into work. Some must remain as heat, at a lower temperature. This asymmetry, this fundamental difference between heat and work, is at the heart of thermodynamics. And it brings us to the man who finally gave entropy its name and its mathematical form. Rudolf Clausius was a German physicist working in the mid-1800s, around the same time that Kelvin was exploring absolute temperature. Clausius took Carnot's insights and Kelvin's mathematics and built them into a complete theory of thermodynamics. And in doing so, He introduced the concept that would become central to all of physics: entropy. The word itself sounds vaguely ominous, doesn't it? Entropy. It has echoes of atrophy or trophy, decay and victory, ending and achievement. Clausius derived it from Greek roots meaning transformation or turning toward. He wanted a word that captured the idea of change, of things moving from one state to another. But what exactly is entropy? Clausius defined it mathematically as the amount of heat transferred in a reversible process, divided by the absolute temperature at which the transfer occurs. But that's an abstract definition, useful for calculations, but not particularly illuminating. Here's a better way to think about it. Entropy is a measure of how spread out energy is, how dispersed, how diluted. Low entropy means energy is concentrated in a small number of ways, in specific places, organized, and available. High entropy means energy is spread out across many possibilities, distributed widely, randomized, and less available for doing work. Let me give you some examples that you can visualize. A hot cup of coffee sitting on a table. At first, the thermal energy is concentrated in the liquid in the cup. The coffee molecules are jittering rapidly. The surrounding air molecules are moving more slowly. There's a clear difference, a clear gradient. This is relatively low entropy. The energy is concentrated in one place. Now wait. Watch. The heat flows from the coffee into the air. Slowly, molecule by molecule, energy spreads outward. The coffee cools. The air near the cup warms slightly. After enough time, the coffee and the air are at the same temperature. The energy that was once concentrated in the cup is now spread throughout the room. Higher entropy. Or consider perfume. You spray it in one corner of a room. Initially, all the perfume molecules are in a small region of space. Low entropy. They're organized, localized, concentrated, but immediately they begin to diffuse. They spread out, carried by air currents and their own random motion. Soon, perfume molecules are everywhere in the room. Each breath you take might contain a few of them, no matter where you're standing. High entropy. The molecules are dispersed, spread out, randomized. In both cases, something has spread from concentrated to dispersed, from organized to randomized, from low entropy to high entropy. And crucially, this spreading happens naturally, spontaneously, without any external intervention. Heat flows from hot to cold. Perfume diffuses from concentrated to dilute. Ink spreads through water. Gases expand to fill their containers. The reverse never happens on its own. Coffee doesn't spontaneously heat itself while cooling the surrounding air. Perfume doesn't gather itself back into the corner where it was sprayed. Scrambled eggs don't unscramble. Why not? Clausius discovered that there's a fundamental law governing this behavior. A law as important as the conservation of energy itself. He expressed it mathematically. But the essence is simple. In any natural process, in any isolated system, the total entropy never decreases. It either stays the same, in perfectly reversible processes, or increases, in all real processes. This is the second law of thermodynamics, and it's one of the most profound statements ever made about the physical universe. The first law says, energy is conserved. You can't create it or destroy it. The second law says, entropy increases. Energy tends to spread out. Organization tends to dissolve. Concentrated becomes dispersed. Together, these two laws explain so much. Why engines can't be perfectly efficient. Because converting heat to work requires decreasing entropy locally, which must be paid for by increasing it more elsewhere. Why you can't unbreak a glass. Because the high-entropy shards won't spontaneously reassemble into the low-entropy intact glass. Why mixing is easy, but unmixing is hard. But there's still a question, a deep question. Why? Why does entropy increase? What's the mechanism? What drives this spreading? This dispersal? This inexorable march from organized to random? Is it a law imposed from outside? A rule the universe must follow? Or is it something more subtle, more statistical? The answer came from a brilliant physicist who understood that the behavior of large systems emerges from the behavior of tiny particles. His name was Ludwig Boltzmann, and his insight would transform our understanding of entropy from something mysterious and almost mystical into something understandable and even inevitable. Imagine again our two metal bars from the Carnot engine thought experiment. One hot, one cold. But now let's zoom in. Let's look at what's happening at the level of individual atoms. The hot bar is composed of atoms that are vibrating intensely. Each atom is jittering in place, bonded to its neighbors, but shaking with considerable energy. The amplitude of these vibrations is large. The atoms are restless. The cold bar's atoms are also vibrating, but much more gently. Smaller amplitudes, less movement, less energy per atom. Now bring the bars into contact. At the boundary where they touch, hot atoms and cold atoms are suddenly neighbors. The hot atoms are vibrating wildly. They collide with the cold atoms. In these collisions, energy transfers. Fast-moving atoms slow down slightly. Slow-moving atoms speed up slightly. It's like billiard balls colliding. Momentum and energy redistribute. After many collisions, and we're talking about trillions upon trillions of collisions happening every second, the energy that was concentrated in the hot bar spreads into the cold bar. Eventually, both bars reach the same temperature, thermal equilibrium. This makes intuitive sense. Energy flows from hot to cold. We've seen it happen countless times. But now comes Boltzmann's brilliant question. Why doesn't it ever happen in reverse? Why doesn't energy ever flow from cold to hot spontaneously? Why don't the slow-moving atoms in the cold bar, through some lucky series of collisions, happen to transfer energy to the hot bar, making the hot bar hotter and the cold bar colder? After all, there's nothing in the fundamental laws of physics that forbids this. Newton's laws of motion work the same forward and backward in time. A collision that transfers energy from fast to slow could, in principle, be reversed. Energy transferring from slow to fast. So why don't we see it? Boltzmann's answer was revolutionary. It's not impossible. It's just incredibly, spectacularly, almost unimaginably unlikely. Let me illustrate with a simpler example. Imagine you have not two bars, but two small boxes. In one box, you have 10 units of energy to distribute among the atoms. In the other box, you have 0 units of energy. If we bring the boxes into contact and allow collisions, the energy will spread. Maybe the distribution becomes 6 units in one box and 4 in the other, or 5 and 5. The exact distribution will fluctuate, but on average, the energy will be roughly equal. Could it spontaneously return to 10 and 0? Sure. It's not impossible. If every collision happened to go just right, if every atom's motion happened to align perfectly, the energy could concentrate back into one box. But as the number of atoms increases, this becomes less and less likely. With 100 atoms, it's very unlikely. With 1,000 atoms, it's extraordinarily unlikely. With a mole of atoms, that's 6 times 10 to the 23rd atoms, roughly the number in a glass of water. It's so unlikely that it would never happen, even if you waited billions of times the age of the universe. Boltzmann made this precise with mathematics. He showed that entropy is related to the number of ways energy and particles can be arranged. The more ways something can be arranged, while still looking macroscopically the same, the higher its entropy. Think of a Rubik's Cube. When it's solved, all sides showing a single color, there's only one arrangement, or a few. If you count rotations, this is low entropy, highly organized, specific. When it's scrambled, there are millions upon millions of arrangements that all look scrambled. This is high entropy. Many possibilities. Generic. If you randomly twist the cube, you're far more likely to end up in one of the millions of scrambled states than in the single solved state. Not because there's a law against solving it randomly. It's just statistically improbable. Scale this up to atoms. A bar of metal has something like 10 to the 23 atoms. The number of ways to arrange their energies is almost beyond comprehension. Most of those arrangements correspond to energy being spread out roughly evenly. Very, Very few correspond to energy being highly concentrated in one region. So when energy spreads from hot to cold, it's not because of some mystical force pushing it that way. It's because there are vastly more ways for energy to be spread out than for it to be concentrated. The system is simply exploring possibilities at random through molecular collisions, and the overwhelming majority of possibilities involve higher entropy. Its probability, statistics, the law of large numbers. Heat flowing from cold to hot isn't impossible. It's just so unlikely that we'd never expect to see it happen naturally, not in any reasonable time frame. This is why eggs don't unscramble, why broken glasses don't reassemble, why mixed paint doesn't separate back into distinct colors. Not because it's forbidden by the laws of physics, but because the number of ways to be broken, scrambled, and mixed vastly exceeds the number of ways to be intact, separated, and organized. Entropy increases because higher entropy states are more numerous, and in a universe governed by random motion, at the microscopic scale, systems naturally drift toward the more numerous states. This is Boltzmann's great insight. Entropy isn't a mysterious force. It's a statistical inevitability. But here's where things get even more interesting. If entropy always increases in isolated systems, and if the universe itself is an isolated system, then shouldn't everything eventually reach maximum entropy? Shouldn't everything spread out, even out, reach equilibrium, and then stop? And if that's true, how can we explain the existence of low-entropy structures, like stars, planets, and life? The answer lies in understanding that Earth is not an isolated system, and neither are you. It's a hot summer day. You're inside an air-conditioned room, comfortable and cool, while outside, the sun beats down mercilessly. The air conditioning hums quietly, doing its work, keeping you comfortable. But think about what's happening inside the room. The temperature is dropping. The air molecules are slowing down. The thermal energy in the room is being reduced. If we consider just the room in isolation, entropy is decreasing. Energy is becoming more concentrated. Heat is being pumped from the cooler inside to the warmer outside, which is the opposite of the natural flow. Wait, didn't we just say entropy always increases? Isn't this a violation of the second law? Not at all. And this is crucial to understand. The room is not an isolated system. The air conditioner is plugged into the wall, drawing electrical power. That electricity is coming from a power plant somewhere, which is burning fuel, or splitting atoms, or harnessing falling water to generate energy. And in all of those processes, entropy is increasing enormously. At the power plant, fuel burns, organized chemical bonds break, concentrated chemical energy spreads out as heat. Some of that heat is converted to electricity, which travels through wires to your air conditioner. The air conditioner uses that electricity to pump heat from inside to outside. The heat gets dumped into the outdoor air, slightly warming the environment around your building. Now let's do the full accounting. Inside your room, entropy decreased. That's real. But at the power plant, entropy increased significantly. Burning fuel, generating heat, converting only a fraction to electricity. In the transmission lines, entropy increased. Resistance causes some energy to dissipate as heat. In the air conditioner itself, entropy increased. The compressor and motors generate friction and waste heat. Outside your building, entropy increased. The heat pumped from your room warms the outdoor air. When you add it all up, the total entropy of the entire system, room, building, air conditioner, power plant, fuel, and environment, has increased. The second law is satisfied. Entropy, overall, went up. This is a profound and general principle. You can create order locally. You can decrease entropy in one place, but only by increasing it more somewhere else. Life itself is an example of this. Your body is a highly organized, low-entropy structure. You're not in thermal equilibrium with your surroundings. You're warmer than room temperature. You're chemically complex. You're structured, ordered, intricate, and yet, you're not violating the second law. How? Because you're not an isolated system. You eat food. That food contains low-entropy chemical energy, organized molecules like sugars, proteins, fats. Your body breaks down these molecules, extracts their energy, uses that energy to maintain your structure, to move your muscles, to fire your neurons, to repair your cells. And in doing so, you increase entropy enormously. You exhale carbon dioxide and water vapor. You radiate heat into your environment. You excrete waste products. All of these outputs have higher entropy than the inputs. The organized energy in your food becomes dispersed heat and disorganized molecules. You are an engine, running on food, maintaining local order. By exporting disorder to your environment, every living thing does this. Plants capture low-entropy sunlight and use it to build ordered structures, like leaves and stems, releasing high-entropy heat in the process. Animals eat plants or other animals, using their low-entropy chemical energy to sustain their own structures. Bacteria, fungi, all of life, every living organism, is a temporary pocket of low entropy, sustained by a flow of energy from organized to dispersed. The pattern is the same everywhere. Order can be created, Structures can be built. Entropy can decrease locally, but only if it's paid for, with an even greater increase in entropy elsewhere. This is not a loophole in the second law. This is how the second law allows complex, interesting things to exist, and it brings us to perhaps the most beautiful question of all. Why does life exist in the first place? Step outside on a clear day. Feel the warmth of sunlight on your skin. Look at a tree growing, a bird flying, a flower blooming. All of this is powered by the sun. Yes, but not in the simple way we usually think. The sun is not just providing energy. Remember, energy is conserved. Energy can't be used up. What the sun is providing is low entropy. Let's trace the journey. Deep in the core of the sun, hydrogen nuclei are slamming together under tremendous pressure and heat, fusing into helium. This fusion releases energy that was locked in the configuration of those nuclei, in the strong nuclear force binding them together. That energy works its way outward, through hundreds of thousands of miles of dense plasma, eventually reaching the sun's surface and radiating into space. By the time it leaves the sun, this energy is in the form of photons, particles of light, and crucially, these are high-energy photons. Visible light, ultraviolet light. Each photon carries a significant amount of energy in a small, concentrated package. These photons travel through the vacuum of space. Some of them, a tiny fraction, happen to strike Earth. When they do, they bring with them concentrated, low-entropy energy. A leaf captures some of these photons through the intricate machinery of photosynthesis. It uses their energy to rearrange molecules. It takes carbon dioxide from the air and water from the soil. Simple, relatively high-entropy molecules, and builds them into glucose, a complex sugar. This glucose is an organized molecule. Its chemical bonds store energy in a concentrated, low-entropy form. The plant uses some of this glucose to build its own structure. Cellulose for cell walls, starches for energy storage, proteins for cellular machinery. The plant grows. It becomes a highly ordered, complex structure. But the plant doesn't keep all the energy. It can't. Some of it is used for cellular respiration, breaking down glucose to power the plant's metabolism. In this process, glucose and oxygen are converted back into carbon dioxide and water, and energy is released as heat. That heat radiates from the plant's leaves, warming the air, spreading into the environment. Now an animal eats the plant. The animal digests the plant's tissues, breaking down the complex molecules into simpler ones, extracting the stored chemical energy. That energy powers the animal's muscles, its heartbeat, It's breathing. It's thinking. The animal moves. It hunts. It reproduces. It lives. And all the while, it's generating heat, radiating warmth into its surroundings, exhaling carbon dioxide, excreting waste products. Eventually, both the plant and the animal die. Decomposers, bacteria and fungi, break down their remains. The complex molecules they spent their lives building are disassembled back into simple components. Nutrients return to the soil. Carbon returns to the air. And heat, always heat. At every step, energy flows and spreads. Concentrated becomes dispersed. Organized becomes random. Low entropy becomes high entropy. Follow the energy all the way through. The photons that left the sun. High energy. Low entropy. Few particles have been converted into many more photons of infrared radiation. Lower energy. Higher entropy. Many particles radiating from Earth back into space. Same total energy. Much higher total entropy. And in the middle of this flow, in the brief period when energy is transitioning from concentrated to dispersed, life exists. Life is what happens in the gradient. Life is what emerges when there's a flow of low-entropy energy passing through a system. Some scientists have proposed that life is almost inevitable, given the right conditions, not because of design, not because of purpose, but because of entropy. When low-entropy energy is flowing through a system, that system will naturally organize itself in ways that facilitate the dissipation of that energy. Structures will form that are good at capturing the inflowing energy and releasing it in a more dispersed form. Living things are very good at this. We're highly efficient at capturing low-entropy energy, food, sunlight, and converting it to high-entropy waste, heat, carbon dioxide, and so on. In the process, we maintain our own internal order, but always at the cost of increasing entropy in our environment by a greater amount. From this perspective, life is not fighting against entropy. Life is a consequence of entropy. Life exists because entropy is increasing. This is a profound reframing. Instead of viewing life as fragile order, desperately struggling against the tide of chaos, we can see life as a natural manifestation of the universe's tendency toward higher entropy. We're not exceptions to the rule. We're examples of the rule in action. But this raises an even deeper question. If entropy is always increasing, if the universe naturally flows toward higher entropy, then why was the early universe in such a low entropy state to begin with? Why did the universe start with concentrated energy, rather than dispersed energy. Why was there order in the first place? This is one of the most profound mysteries in cosmology, and the answer, or at least the beginning of an answer, has to do with gravity and the shape of the universe itself. Imagine you could rewind time all the way back, past the evolution of life, past the formation of Earth, past the birth of the Sun, past the formation of galaxies, past the first stars, back to the very beginning, 13.8 billion years ago. The universe began in a state we call the Big Bang, not an explosion in space, but an expansion of space itself. In the earliest moments, everything was compressed into a volume almost infinitesimally small, hot beyond imagination, dense beyond comprehension, and then expansion. Space grew, energy spread, temperature dropped. Within the first few minutes, the universe cooled enough for protons and neutrons to stick together, forming the first atomic nuclei, mostly hydrogen, some helium, trace amounts of lithium. For hundreds of thousands of years, the universe was too hot for atoms to form. It was a plasma, a soup of nuclei and electrons, opaque to light, glowing white-hot. Then, around 380,000 years after the Big Bang, the universe cooled enough for electrons to bind to nuclei. Atoms formed. The plasma became transparent. Light could travel freely. The universe went from opaque to clear, and the cosmic microwave background radiation was released. The afterglow of the Big Bang, which we can still detect today. At this point, the universe was remarkably uniform, nearly the same temperature everywhere, nearly the same density everywhere. Slight variations, tiny quantum fluctuations, stretched to cosmic scales by inflation, but overall, surprisingly smooth. And here's the puzzle. This seems like a high-entropy state. Everything mixed together. Energy spread out evenly. No structure. No order. Maximum entropy. Right. Wrong. And this is where our intuition about entropy can mislead us. For a universe containing only matter and radiation, and no gravity, yes, a smooth, evenly distributed state would be high entropy. But our universe has gravity, and gravity changes everything. Gravity is an attractive force. Mass pulls on mass. And this means that for a gravitational system, a smooth, evenly distributed state is not the highest entropy state. It's actually a very low entropy state. Think about it this way. If you have a bunch of particles spread evenly through space, and you let gravity do its thing, what happens? The particles start to pull on each other. slight overdensities, regions with just a little bit more mass, pull in more material. The dense regions get denser. The sparse regions get sparser. Over time, the smooth distribution clumps. Matter collapses into concentrations. Stars form. Galaxies form. Structure emerges. And this increases entropy. It seems backward at first. How can clumping increase entropy? Isn't clumping the opposite of spreading out? But remember, entropy is not just about spatial distribution. It's about the number of possible arrangements, the number of microstates corresponding to a given macrostate. For a gravitational system, clumped configurations vastly outnumber smooth configurations. When you account for all the possible ways particles can move and arrange themselves, a galaxy with stars orbiting in complex trajectories has many more possible detailed configurations than a smooth cloud of gas. Moreover, as matter clumps under gravity, it releases gravitational potential energy. That energy becomes heat. Temperature rises. Eventually, fusion ignites in the densest regions. Stars are born. Stars radiate energy into space. That radiation disperses, spreads out, increases entropy enormously. So gravity does something fascinating. It turns a smooth, low-entropy initial state into a clumpy, structured, higher-entropy state. And in the process, it releases energy in forms that can power complexity. The early universe was not in equilibrium. It was in a very special, very unlikely, very low entropy configuration. Smooth, yes, but smooth in a way that had enormous potential for structure to form under the influence of gravity. Why? Why did the universe start that way? We don't fully know. This is sometimes called the past hypothesis, the assumption that the universe began in an extremely low entropy state. It's one of the great unsolved questions. In cosmology, some theories suggest it has to do with the initial conditions of the Big Bang itself, perhaps related to inflation or quantum effects. Others propose that our universe might be part of a larger multiverse, and we happen to exist in a region with low initial entropy, simply because high entropy regions don't give rise to complexity or observers. But whatever the reason, the fact remains, the universe started with low entropy, and it has been increasing in entropy ever since. And all the structure we see, stars, galaxies, planets, life, is a consequence of that journey from low to high entropy. Let's dive deeper into this strange relationship between gravity and entropy, because it's central to understanding why the universe looks the way it does. Imagine a vast, empty region of space. Now place a cloud of gas particles in it, spread evenly throughout the volume. The particles have some small amount of random motion, but overall, they're distributed uniformly. In a universe without gravity, this is a high entropy state. The particles are spread out. Energy is distributed evenly. Nothing particularly interesting is happening, and nothing particularly interesting will happen. The particles will just continue to drift randomly, maintaining roughly the same uniform distribution, but add gravity. Now each particle is pulling on every other particle. The force is weak. Gravity is by far the weakest of the fundamental forces, but it's always attractive, and it acts over infinite distances. Initially, the pull is nearly balanced in all directions because the distribution is uniform. But remember those tiny quantum fluctuations I mentioned earlier, those tiny variations in density from place to place. Gravity amplifies them. A region that's slightly denser than average has slightly more mass, which means slightly more gravitational pull. It attracts particles from neighboring regions. As it does, it becomes even denser, which increases its pull, which attracts more particles. This is called gravitational instability, and it's a runaway process. The dense regions get denser. The sparse regions get sparser. The smooth cloud begins to fragment into clumps. Inside each clump, gravity continues to pull inward. The clump contracts. As it contracts, gravitational potential energy is converted into kinetic energy. The particles move faster. As they fall inward, their temperature rises. If the clump is large enough, this heating continues until the core reaches millions of degrees. At that point, hydrogen nuclei start fusing into helium. Nuclear fusion ignites. A star is born. The star radiates energy into space. Photons stream outward in all directions, carrying energy and entropy away from the star and into the void. This is crucial. The star is a low-entropy object. It's highly organized, with fusion occurring in the core, energy flowing outward through layers of plasma, a temperature gradient from the hot core to the cooler surface. But by radiating energy into space, the star increases the entropy of the universe as a whole. by an enormous amount. Meanwhile, on larger scales, clumps of matter are merging, colliding, forming galaxies. Stars orbit. Within these galaxies, some stars form planetary systems. Some planets develop atmospheres, oceans, continents, and if the conditions are right, if there's a stable orbit around a long-lived star, if there's liquid water, if there are the right chemical ingredients, life might emerge. All of this structure, all of this complexity arises because gravity takes a smooth, low-entropy initial state and evolves it toward a clumpy, structured, higher entropy state. This is so counterintuitive that it's worth pausing to absorb it in everyday experience. Spreading out increases entropy. Mixing increases entropy. But for a gravitational system, clumping increases entropy. Why? Because when you account for the motion of particles, for the energy released in the process of clumping, for the radiation emitted by hot, dense objects, the total number of possible microstates, the total number of ways the system can be arranged, is vastly higher in the clumped state than in the smooth state. A galaxy full of stars, each with its own orbit, its own history, its own evolution, has far more entropy than a smooth cloud of gas. Gravity doesn't violate the second law. It obeys it in a way that happens to create beautiful, complex structures. And the most extreme example of this, the ultimate endpoint of gravitational collapse, is the black hole. In the 1970s, a young physicist named Jacob Bekenstein was studying black holes. These were theoretical objects at the time, predicted by Einstein's general relativity, but not yet observed directly. A black hole forms when a massive star collapses at the end of its life, compressing so much mass into such a small volume that the gravitational pull becomes inescapable. Not even light can escape from within the event horizon. Black holes were mysterious. They seemed to violate the second law of thermodynamics. Here's why. Imagine you have a room full of gas at a certain temperature and entropy. Now imagine you throw that gas into a black hole. The gas crosses the event horizon and disappears from the observable universe. All the information about the gas's entropy seems to be lost. The black hole gains mass, but it appears to have no other features. It's described entirely by its mass, charge, and rotation. Nothing else. No temperature. No entropy. Just mass. Charge. Spin. This seemed to suggest that you could decrease the entropy of the universe by throwing things into black holes, which would violate the second law. Bekenstein proposed a radical solution. What if black holes themselves have entropy? What if the event horizon, the boundary of the black hole, has an entropy proportional to its area? At first, this seemed absurd. How can a featureless, smooth surface have entropy? Entropy is supposed to count microstates, possible configurations. A black hole is the simplest object imaginable. What microstates could it possibly have? But Bekenstein argued that the idea was necessary to preserve the second law. When you throw matter into a black hole, the black hole's area increases if that area has entropy, and if the entropy increase of the black hole exceeds the entropy decrease of the matter you threw in, then the total entropy of the universe still increases. Most physicists were skeptical, including Stephen Hawking. Hawking set out to disprove Bekenstein's idea, but in doing so, he discovered something even more remarkable. Using quantum field theory in curved spacetime, Hawking calculated what would happen near the event horizon of a black hole. Quantum mechanics says that even in empty space, particle-antiparticle pairs are constantly popping into existence and annihilating each other. This happens everywhere, all the time, as a consequence of Heisenberg's uncertainty principle. Near the event horizon, something strange can happen. A particle-antiparticle pair can form right at the boundary. One falls into the black hole. The other escapes to a distant observer. It looks like the black hole is emitting radiation. This is Hawking radiation, and it has a temperature. The temperature is incredibly small for large black holes. For a black hole the mass of the Sun, the Hawking temperature is 100 millionth of a degree above absolute zero. For the supermassive black hole at the center of the Milky Way, 4,000,000 times the mass of the Sun, the temperature is even lower. But the fact that black holes have a temperature at all is profound, because anything with a temperature has entropy. The first law of thermodynamics connects energy and temperature. The second law connects temperature and entropy. Hawking's calculation confirmed Bekenstein's intuition. Black holes have entropy, enormous entropy. The entropy is proportional to the area of the event horizon, measured in Planck units, the smallest possible meaningful length in quantum gravity. For the black hole at the center of our galaxy, the entropy is almost unimaginably large, around 10 to the 90th power. That's a 1, followed by 90 zeros. To put that in perspective, the total entropy of all the stars, planets, gas, and dust in the entire visible universe is far, far less than the entropy of a single supermassive black hole. Black holes are the highest entropy objects that can exist in a given volume of space. This is astonishing. Black holes are the final state of gravitational collapse. They're what you get when you compress matter to its ultimate density, and they represent the maximum possible entropy for that mass. From the perspective of thermodynamics, black holes are not strange anomalies. They're the endpoint, the most probable final state, the configuration toward which gravitational systems naturally evolve. Stars are temporary, planets are temporary, galaxies are temporary, but black holes, at least until they evaporate via Hawking radiation over timescales vastly longer than the current age of the universe, are closer to the ultimate high-entropy state. And this tells us something profound about the future of the universe. Fast forward, not millions of years, not billions, trillions upon trillions of years, into the future. The universe is still expanding. In fact, the expansion is accelerating, driven by dark energy, a mysterious property of space itself that pushes galaxies apart. Stars are still forming, but at a much slower rate than today. The clouds of gas from which stars form are being exhausted. The largest, brightest stars have long since burned out, dying in supernova explosions or collapsing into black holes. Smaller stars, red dwarfs, linger longer. They burn their fuel slowly, sipping hydrogen over timescales of tens of trillions of years. But eventually, even they exhaust their fuel and fade. Around 10 trillion years from now, the last star will burn out. The universe will go dark, but it's not over yet. Dead stars remain. White dwarfs neutron stars, black holes, planets orbit. In the darkness, galaxies, now starless, still hold themselves together through gravity, at least for a while, over unimaginable timescales, 10 to the 26th years or more. Even these galaxies will disperse. Stars, long dead, will be ejected from their galaxies through random gravitational encounters. Some will be flung into intergalactic space. Others will fall into the central black holes. The black holes grow. They consume whatever falls into them. They merge with other black holes. Slowly, over eons, larger and larger black holes form. But black holes are not eternal. Hawking radiation means they evaporate. Slowly, incredibly slowly, they lose mass. A black hole, the mass of the Sun, would take 10 to the 67th years to evaporate. A supermassive black hole would take even longer, 10 to the 100th years or more. But eventually, even they will vanish. They'll radiate away their mass as photons and particles, dispersing their entropy into the void. What's left? A vast, expanding space filled with radiation, photons stretched to enormous wavelengths by the expansion. Occasional particles, electrons, positrons, neutrinos, separated by distances larger than galaxies are today. Everything at nearly the same temperature, a tiny fraction of a degree above absolute zero. This is the heat death of the universe. Not a dramatic end, not a fiery collapse, just a slow fade into equilibrium. In this far future, there are no gradients, no flows of energy from hot to cold, no concentrated sources of low entropy. Everything is spread out, mixed, uniform. Entropy has reached its maximum, and in this state, nothing happens. There are no stars to shine, no chemical reactions to power life, no processes to drive change. Time, in a meaningful sense, ceases to have an arrow. The future becomes indistinguishable from the past. There's no difference between before and after, because nothing changes. This might sound bleak, depressing, even the ultimate fate of everything we know. Silence, darkness, cold. But consider the scale of time. We're discussing 10 to the 100th years. That's not just longer than the current age of the universe. It's longer by a factor so large, it's almost meaningless to comprehend. The current age of the universe is about 14 billion years. We're talking about timescales. A trillion times longer for all practical purposes. From the perspective of anything remotely resembling human experience or even cosmic experience, the heat death is infinitely far away. And before then, now, in this current epoch, this brief window, when stars shine, and planets orbit, and life exists, there is time, vast amounts of time, billions of years, of stellar evolution ahead, countless worlds, yet to form, civilizations, yet to rise. We exist in the middle of the story, in the era of complexity, in the era when entropy is increasing, but hasn't yet reached its maximum, when there are still gradients, still flows, still low-entropy energy, driving interesting processes. This is the sweet spot, the narrow window, when the universe is neither too ordered nor too disordered, when there's just enough structure for fascinating things to happen. And that brings us back to the deepest question of all. Why does time feel like it flows forward? Why do we experience past and future as fundamentally different? You remember yesterday. You remember what you ate for breakfast, who you talked to, what you did. The memories are there, accessible, stored in the neural patterns of your brain. You don't remember tomorrow. You don't know what you'll eat for breakfast tomorrow, who you'll talk to, what you'll do. The future is unknown, uncertain, open. This asymmetry, this difference between past and future, seems so fundamental that we rarely even question it. Of course, we remember the past and not the future. That's just how time works. But why? The fundamental laws of physics don't have this asymmetry. Newton's laws work the same forward and backward in time. Maxwell's equations of electromagnetism are time reversible. Even Einstein's general relativity and the equations of quantum mechanics don't inherently distinguish past from future. If you recorded the motions of particles in a closed system and played the recording backward, the laws of physics would still be obeyed. Nothing in the fundamental equation says time must flow this way and not that way. And yet, in our experience, time has a clear direction. The arrow of time points from past to future. Always. We age. In one direction, eggs scramble, but don't unscramble. Glasses break, but don't spontaneously repair themselves. Why? The answer is entropy, the arrow of time. The reason we experience past and future as different is intimately connected to the fact that entropy increases. Here's how it works. Imagine a glass of water with an ice cube in it. Right now, in the present moment, the ice cube is melting. The water is slightly warmer than the ice. Heat flows from the water into the ice. The ice molecules gain energy. Their crystalline structure breaks down, and they join the liquid water surrounding them. Entropy is increasing. The organized, low-entropy solid is becoming disorganized. Higher-entropy liquid. Now ask yourself, how do you know this is happening now, and not in reverse? How do you know you're not watching a film played backward, where water is freezing into an ice cube? You know, because of entropy. The melting process increases entropy. The freezing process would decrease entropy. And in a closed system, entropy doesn't spontaneously decrease. The direction of entropy increase defines the arrow of time. When you remember the past, you're accessing stored information in your brain. That information is there because of causal processes that happened earlier. Events left imprints. Photons from the sun bounced off objects and into your eyes. Neurons fired in response. Synaptic connections strengthened. Patterns were encoded in the structure of your brain. All of those processes involved entropy increase. The low-entropy photons from the sun were absorbed and converted to heat. The chemical reactions in your neurons dispersed energy. The act of forming a memory is an irreversible process that increases entropy. You can't remember the future because those causal processes haven't happened yet. The future hasn't left its imprint on the present. Information flows from past to future, not the other way around, because entropy flows from low to high. This is why cause precedes effect. It's why we can influence the future, but not the past. It's why we feel time moving forward. It's all because of entropy. But here's the truly deep part. If the universe were in a maximum entropy state, if everything were perfectly mixed, perfectly equilibrated, there would be no arrow of time. The future would be the same as the past. Nothing would change. There would be no memory, no causation, no sense of before and after. The arrow of time exists only because the universe is not in equilibrium, only because entropy is still increasing, only because we live in a special epoch between the low-entropy Big Bang and the distant, high-entropy heat death. We exist in the gradient, and the gradient is what makes time meaningful. This is humbling and awe-inspiring. At the same time, our entire experience of reality, our memories, our choices, our sense that time flows, is contingent on the fact that the universe started in a low-entropy state and is evolving toward a high-entropy state. We're riding the wave of increasing entropy, and that wave is what gives time its direction. Let me tell you about a cup of tea. You've just poured hot water into a cup. Now you add a drop of milk. At first, the milk sits in the water as a distinct white droplet, concentrated, localized, low entropy. Then it begins to spread. Tendrils of white curl through the tea, forming intricate, swirling patterns, spirals, wisps, eddies. The shapes are beautiful, complex, ever-changing. Watch. For a few moments, the patterns evolve. The milk disperses further. The swirls become more intricate, then less so. Eventually, the milk is fully mixed. The tea is now a uniform tan color, homogeneous, high entropy. Now think about this process in terms of entropy. At the very beginning, when the milk was a single drop, the entropy was low. There was order, structure, a clear separation between milk and tea. At the very end, when the milk is fully mixed, the entropy is high. But interestingly, the final state is also simple. It's just uniform tan liquid. There's no structure, no patterns. It's boring. The beautiful part, the swirls, the patterns, the complexity exists in the middle, in the transition from low entropy to high entropy. This is profound. Both very low entropy and very high entropy are simple, ordered in one case, fully mixed in the other, but simple either way. Complexity exists in between. Think about the universe. At the very beginning, just after the Big Bang, everything was simple, uniform, a smooth plasma of particles and radiation, low entropy, but simple. At the very end, in the heat death, everything will again be simple, uniform, a smooth bath of radiation and occasional particles, high entropy, but simple. But now, in the middle, the universe is complex. Galaxies, stars, planets, moons, atmospheres, oceans, weather, chemistry, life. All of this complexity exists because we're in the middle of the entropy gradient. We're in the transition zone, where the universe is neither too ordered nor too disordered. Consider life. Specifically, life requires certain conditions. It needs energy gradients, like the flow of sunlight from the sun to Earth. It needs chemical disequilibrium, nutrients in one place, waste in another, concentrations that drive reactions. It needs low entropy inputs to maintain its structures. Too early in the universe, in the first few 100,000 years, and it's too hot and uniform for complex chemistry. Atoms haven't even formed yet. Too late in the universe, trillions of years from now, and all the stars have burned out. All the energy gradients have dissipated. There's no low entropy fuel to power life. Life exists in the middle, in the Goldilocks zone of cosmic time, when the universe has cooled and structured enough for stars and planets to form, but hasn't yet equilibrated completely. And not just life in general, complex life, conscious life, intelligent life. We are living in the most complex era of the universe, the era when matter has organized itself into intricate patterns, when atoms have arranged into molecules, molecules into cells, cells into organisms, organisms into ecosystems, ecosystems into biospheres. When energy flows through these systems, maintaining order locally while increasing entropy globally, when the patterns are most beautiful, like the swirls of milk in tea, we exist in the transition. We are the complexity that emerges when entropy is increasing but hasn't yet reached its maximum. This is not an accident. This is not, despite the second law of thermodynamics. This is because of it. Complexity arises in the gradient. Beauty emerges in the transition. Life flourishes in the flow from low entropy to high entropy. We are the swirls in the cosmic cup of tea. Temporary, yes, fleeting on the timescale of eternity, but real, intricate, meaningful, and that's worth appreciating. What does it mean to be alive? From a physics perspective, it means you're a temporary pocket of low entropy, a highly organized structure maintained by a constant flow of energy. You eat food, low entropy chemical energy. You metabolize it. You use it to power your cells, your muscles, your brain, and you exhale, excrete, radiate heat, high entropy waste. You are, in essence, a dissipative structure, a pattern that maintains itself by dissipating energy. But you're not just any pattern. You're conscious. You think. You feel. You wonder about your place in the universe, and the fact that you can do these things is directly related to entropy. Your thoughts are patterns of neural activity, electrical signals cascading through networks of neurons, synapses firing in particular sequences. These patterns require energy to maintain. They require organization. They require low entropy. Every time you form a memory, you're creating structure. In your brain, you're decreasing local entropy by encoding information in the strength of synaptic connections. But to do that, you had to burn glucose, generate heat, increase entropy in your environment by a greater amount. Every time you make a decision, you're processing information, weighing options, predicting outcomes. This requires computation, which requires energy dissipation, which increases entropy. Even the fact that you experience time as flowing forward, that you remember the past but not the future, is a consequence of entropy. In a very real sense, you are entropy in action. You are the universe increasing its entropy in a particular, interesting way. And so is everyone else. Every person you know, every animal, every plant, every ecosystem, all of life is the universe, finding pathways to higher entropy. We're not fighting entropy, we're writing it. But here's what's beautiful in riding this wave. We create meaning, we build, we learn, we love, we make art, music, science, poetry. We form communities, we tell stories, we care, about each other. None of this violates the laws of thermodynamics. None of this stops entropy from increasing, but all of it is real. All of it matters. The paintings of Van Gogh exist because of low-entropy energy from the sun filtered through Van Gogh's metabolism, channeled through the neurons in his brain, translated into the movement of his hands. The second law was satisfied. More entropy was created than destroyed, but the paintings remain beautiful, meaningful, valued. The music of Beethoven, the equations of Einstein, the poems of Rumi, the pyramids of Egypt, the cathedrals of Europe, the gardens of Kyoto, all of these are temporary structures maintained for a while against the flow of entropy, destined eventually to erode and fade. But that doesn't make them less real. It makes them precious. You are precious for the same reason. You are a pattern that will not last forever. Your body will age. Entropy will accumulate. Cells will fail to repair themselves. Gradually, the organization that makes you you will dissolve. But right now, you exist. You are conscious. You are experiencing this moment, and that moment is powered by the flow of entropy, by the fact that the universe is not in equilibrium, by the fact that low-entropy energy is flowing through the system that is you. In a strange way, entropy gives us the gift of time. If the universe were at maximum entropy, there would be no change, no events, no experiences. Time would be meaningless. But because entropy is increasing, because we live in the gradient, time is real, change is real, life is real, and with life comes possibility, the possibility to think new thoughts, to feel new emotions, to create new things, to love, to learn, to grow. All of this is temporary. All of this is contingent on a universe that started in a low-entropy state and is evolving toward a high-entropy state. But it's not less meaningful because it's temporary. If anything, it's more meaningful. A flower is beautiful partly because it blooms for only a short time, A sunset is precious, partly because it fades into night. A moment of connection with another person is valuable, partly because it's fleeting. Entropy doesn't diminish the value of existence, it defines it. We are the universe, becoming aware of itself for a brief time in a narrow window of cosmic history, in the middle of the great transition from order to disorder. And in that brief time, we can choose how to ride the wave. We can build things that matter. We can seek understanding. We can create beauty. We can reduce suffering. We can expand compassion. We can push the boundaries of what's possible. Not forever, not permanently, but for now. And now is what we have. This is the philosophical heart of entropy. It's not a story of doom. It's not a tale of inevitable decay. It's a recognition that we exist in a universe governed by beautiful, elegant laws that allow for complexity, consciousness, and meaning, laws that give time its arrow and life its possibility. Entropy is not the enemy. Entropy is the stage on which the drama of existence unfolds, and we are part of that drama, active participants, not passive victims of cosmic forces, but conscious beings capable of understanding those forces and finding our place within them. That's the gift. That's the wonder. We live in the gradient, and the gradient is beautiful. So here we are, back where we started. You, perhaps sitting with a cup of tea, the liquid cooling slowly as you read, heat flowing from the cup into the air, never to return, entropy increasing gently, irreversibly. But now you see it differently. That cooling cup is not just a simple, mundane event. It's a microcosm of the entire universe, a demonstration of the fundamental law that governs everything, from the smallest atom to the largest galaxy. Energy spreads, organization dissolves, concentrated becomes dispersed, low entropy becomes high entropy. But in that process, in that flow, in that transition, everything happens. Stars ignite in the depths of collapsing gas clouds, their fusion powered by the conversion of concentrated matter into dispersed energy. Planets coalesce from disks of debris, their landscapes shaped by the flow of heat. From their interiors, life emerges wherever there's a gradient of low-entropy energy, wherever there's a pathway for organization to arise and persist, at least for a while. Consciousness awakens in structures complex enough to process information, to form models of the world, to ask questions about existence and time itself, gains meaning, gains direction, gains an arrow. All of this because entropy increases. All of this because the universe is not in equilibrium. All of this because we live in the middle of a long, slow, beautiful transformation. Entropy is not destruction. Entropy is transformation. It's not chaos. It's the natural tendency for energy to explore all possible configurations, to spread into all available states, to flow from concentrated to dispersed. And we, you, me, every living thing, every star, every galaxy, are part of that flow. When you breathe, you are taking in low-entropy oxygen and exhaling high-entropy carbon dioxide. When you think, you are dissipating energy, creating heat, increasing entropy. When you move, when you eat, when you love, when you create, you are a participant in the grand process of the universe, increasing its entropy. But you're not just passively increasing entropy. You're doing it in a way that creates meaning, beauty, understanding. You're one of the ways the universe has found to increase entropy while simultaneously creating complexity, consciousness, and wonder. Every sunset you watch is photons, low-entropy energy from the sun, scattering through the atmosphere, painting the sky in shades of orange and pink before dispersing into the void, entropy increasing and creating beauty in the process. Every heartbeat is your body using low-entropy chemical energy to maintain the organized structure of your cells, your tissues, your organs, entropy increasing and sustaining life. In the process, every thought you think is neurons firing, signals propagating, patterns forming and dissolving, entropy increasing and generating consciousness. In the process, this is the silent flow of the universe, the gentle, inexorable drift from what was to what must be. The reason the past is different from the future, the reason time has an arrow, the reason you exist at all, and it's beautiful, not in spite of being temporary, but because of it, because you are here, now, in this moment, in this narrow window of cosmic time, when complexity is possible, when stars still shine, when planets still orbit, when life still flourishes. You are a wave in the ocean of entropy, a ripple in the flow of energy through space and time, a pattern that emerged briefly in the transition from order to disorder, and while you exist, you can choose what that pattern does, how it interacts with other patterns, what it creates, what it values, what it loves. The universe started in a low-entropy state 13.8 billion years ago. It will end in a high-entropy state trillions upon trillions of years from now. But between those bookends, in the middle, there is time, there is change, there is possibility, there is you. So the next time you hold a cooling cup of coffee, or watch a candle burn, or feel the warmth of sunlight on your skin, remember what you're witnessing. You're watching entropy in action, the fundamental process that makes time real, that makes life possible, that makes the universe interesting. You're seeing the silent flow, the gentle transformation, the beautiful, inevitable spread of energy from concentrated to dispersed, and you're part of it, not a victim of cosmic forces beyond your control, but a conscious participant in the grandest story ever told, the story of a universe transforming itself slowly, elegantly, one moment, one breath, one heartbeat at a time, from order to disorder, from low entropy to high entropy, from the Big Bang to the heat death. But in the middle, here, now, there is light, there is warmth, there is life, there is you, and that is the most beautiful consequence of entropy, of all. And now, as the universe continues its quiet expansion, as stars burn and fade without intention, as energy spreads patiently into space, there is nothing that needs fixing, nothing that must be saved, nothing that requires urgency. Entropy does not rush. It does not judge. It does not demand meaning. It simply continues. Heat moves where it can. Structures persist while they are able. Patterns form and dissolve. Without preference, the night sky does not collapse. When stars go dark, it just becomes quieter. Processes slow. Gradients flatten. Motion softens. Your body is part of this. Chemical reactions easing. Signals reducing. Systems entering lower activity. Breath continues. Without instruction, heartbeats follow familiar rhythms. Nothing forced, nothing dramatic. Thoughts may appear or not. Both are acceptable. Sleep is not escape, not surrender, just a temporary, low-energy state. Like a forest at night, like an ocean at rest, like matter waiting in equilibrium. There is no lesson, no final realization, only participation. You are not outside the process. You are within it. And as entropy continues its quiet work, you may also let go. Without effort, without resistance, not ending, not beginning, just a pause within a universe that is still becoming. Good night and rest inside the gentle flow of everything continuing as it always has.